So welcome to another video of Chemo topic, and in this video we are going to discuss about the further about the different kind of projection. So in the last class we have discussed about the flying wedge projection in C1 kind of molecule, right, which was the basic molecule, and we know about the now we know about the trick as well. So we are going to use that trick further on. So let's recapitulate something which we have discussed in the last lecture. So we have discussed about flying wedge to we have discussed about flying wedge to Fisher projection conversion, right? So we have discussed about sorry, okay, flying wedge to Fisher conversion, right? Let's take an example and recapitulate the previous discussion. Okay, fine. Now let's take a molecule like C methyl bromine. This is above the plane fluorine and below the plane chlorine. So the rule was like we have to change the direction of the above atom, right, above the plane atom. So the rule was we have to change the direction. We have to change the direction of above group, the group which is present in above the plane, above group. Okay, fine. Now you can see it that this is on the plane, this is all the plane. Okay, methyl and bromine on the plane. So for that, this above and below the plane are on the left hand side. So we can write it over here that this part is on the left hand side. So this part is on the left hand side. So we have to place this above atom into the right hand side into the Fisher projection. So if we draw the Fisher projection of it, then we have to take this on the plane atoms like in this way in a linear manner, and we have to we have to place this above the plane atom in the right hand side because we have to change the direction. So the fluorine is on the right hand side and the chlorine will be added. Okay, fine. So it was our previous discussion. Now it is a C1 carbon. So basically this junction, it is the this carbon atom. Okay, and these are the side atom. So that is why I was telling in the last lecture that it is a C1 kind of molecule. But if we increase the chain length, that is, if this C1 like this one, if these are all the carbon atoms. So if number of carbon atom increases, how to approach? So the trick will be same, and let's discuss further on. And the things will be quite similar. Okay, so how to approach? So let's take a example. Let's suppose we have this kind of molecule. Okay, let's try from the C2. It will be easier for you guys. So one, okay. So this is methyl, this is ethyl. You all know about the bond notation, right? I will explain anyways. So here the substituents are one in above the plane and one in below the plane. Let's take Cl as above the plane and Br as below the plane. So this is one carbon atom, and here also one will be the above, something like this, and one will be the below. So let's take here iodine as the above and fluorine as the below. Now it is a flying wedge projection, you all know. So how to convert it into the 2D Fisher projection, right? We have to convert it into the Fisher projection. So for that reason, we know that we have to fix the on the plane bond length in a linear way. So on the plane is, this is the carbon backbone, right? Methyl to ethyl. This is the carbon backbone, we can see. So let's write it down. So the carbon backbone is like methyl. Okay, let me change the pen. Okay, so it is methyl and ethyl. So I am fixing the on the plane substituents and in a linear manner. Now there are two carbons, right? So 1, 2, C2. So there will be two carbon like this one. So it is C1, it is C2. If I name this as C1 and it is C2, this carbon, then it is adjacent to the methyl group. So this carbon is C1 and this carbon is C2. Okay. Now C1 contains two substituents, right? One chlorine and one bromine. So we have to see the molecule in a similar way, that for this concave, okay, okay. So for this concave, this position are in the right hand side. Why I am telling so? As we are fixing methyl in the top position, so we have to see in this way, right? Fine. In this way we have to see the molecule, and in this way we can see that this position, this above the plane and below the plane, are in the right hand side. And if we see this on the plane like this way, then these two groups which are above and below in the C2 carbon will be placed in the left hand side, right? So let's think that, so this one, these are in the right hand side, and this is in the left hand side, as we are fixing our methyl in the top. Okay, if we okay, so for this one, this part is in the right hand side, this part is in the left hand side. So we have to change the direction of the above the plane atom. So here the above the plane atom is chlorine, and it is in the right hand side of the concave. That is why we have to place it in the left hand side. So we have to place chlorine here in the left hand side, and bromine we have to fix it as it is because it is the below the plane. And for this C2 carbon, this above the plane is situated in the left hand side. So we have to change the above the plane position to the right hand side of the Fisher projection, and we have to keep it as it is fluorine. So this is the Fisher projection of it. Okay, okay. Now I will take the same molecule and try to, okay, try to do in a different way. Mhm. Okay, let me draw another time then. So methyl, ethyl, right? Chlorine, bromine. Here above the plane is iodine and below the plane is fluorine. Okay, now let's try to make the Fisher projection, but now I will see from this direction. So we are consisting this ethyl group in the fixing this ethyl group in the bottom position. So what will be the structure right now? So we have to place it in the bottom, in the top ethyl group, and methyl in the bottom. Now there are two carbons, C1 and C2. In this case, is this is C1, then it is the C1, right? And if this carbon is C2, If this carbon is C2, then it is C2. Fine. So now let's look in the C1 direction. If I draw it like we are fixing the ethyl in the top, so we are seeing this molecule in this direction, so for that, these groups are in the right hand side of the concave and these groups are on the left hand side of the concave. So this will be the in the left hand side, right? These are in the left hand side and these are in the right hand side of the concave. So we have to change the position of the above the plane group. It is in the right hand side, so in Fisher projection we have to place it in the left hand side, and fluorine will be keep as it is. For C2 position, this chlorine atom is above the plane group and it is in the left hand side, so we have to keep it in the right hand side, and bromine we have to keep as it is. Okay, let's try to draw uh, some more molecule like this way. Okay, so let me draw. Okay, now fine. Now let's make the stereochemistry. So above the plane group, below the plane group, above the plane group, below the plane group, above the plane group, below the plane group, above the plane group, below the plane group. Okay, same thing is here as well. Above and below. We have to stick to our rule. That is the trick. Fine. Okay. So let's put the atoms over here. So this will be, let's suppose this is fluorine, this is chlorine, this is bromine, this is iodine, and this is methyl, this is ethyl, and this is, let's suppose it is OH, any kind of group you can place, and this is hydrogen. Okay, fine. This is hydrogen, this is ethyl, this is methyl, bromine, fluorine, chlorine, chlorine, iodine. Like this way, this is methyl, this is chlorine, this is bromine, iodine, F, and OH. Okay, so now let's convert it to the Fisher projection in the same way. Okay, so let's fix our direction first. So we are just seeing the molecule in this way. Okay, from this to this direction, from this to this direction, that means we have to keep this group in the top. Okay, fine. So let's make the Fisher projection. So this part is, it is methyl and it is also methyl, right? It is methyl, it is methyl, it is methyl, and it is also methyl. Okay, so we have to fix it like this one, methyl. So this methyl is that methyl. Okay, now let's draw a line. So we have to 1 2 3 4. Okay, so we have to make 4 bonds. 1 2 3 4. Okay, so here also it is, so this methyl is this one. So we are seeing the molecule from this way to this way. Okay, so if we see the molecule from left hand side to right hand side, then this position will be in the right hand side of the concave, right? So this is the right hand side and this is the left hand side. Fine. So in the first C1 carbon, that is this one, the fluorine is on the right hand side, so we have to keep it in the left hand side. Okay, and Cl. Here the bromine is in the left hand side, so we have to keep it in the right hand side. Bromine, iodine. Fine. For the next carbon, we can see that methyl above the position atom is in right hand side of the concave, so we have to place it in the left hand side, and we have to keep the ethyl as it is, right? For the next carbon, we can see that the above the plane is situated in the left hand side of the concave. This side is the left hand side because we are seeing the molecule from this end to this end. So the OH is on the left hand side, we have to keep it in the right hand side of the concave. Now it is your Fisher projection, right? So just we are changing the position or direction of above group. Okay, okay. So let's try for the next molecule in a similar way. So 1, 2, 3, 4. 1, 2, 3, 4. Okay. So it is methyl and it is also methyl. We are seeing the molecule from left hand side to right hand side. That means this side of the concave will be right hand side and this side of the concave will be left hand side. Fine. So we can see in this carbon above the plane group is hydrogen, which is situated in the right hand side, so we have to keep it in the left hand side of the Fisher projection, and another group is ethyl. Okay, okay. Now for this carbon, the above the group is methyl, which is situated in the left hand side of the concave, so we have to change the direction to the right hand side and the Br will be fixed. Fine. For the next carbon, you can see the above the place is in the right hand side, so we have to keep it in the left hand side, and chlorine. And the last carbon, the Cl is the above the group and it is situated in the left hand side of the concave, so we have to place it in the right hand side and fix the iodine group over here. Okay, so this will be the Fisher projection. So let's try the next molecule. You can pause the video and try it by your own. Okay, so there will be C1, C2 and C3. So C1, C2 and C3. Okay, fine. So this is methyl and this is also methyl. So for this carbon, this side of the concave is left hand side and this side of the concave is right hand side, like the previous one. Okay, so this methyl is in the left hand side above the plane, so we have to keep it in the right hand side in the Fisher projection, right? So this will be the methyl position. Methyl position. Is it clear? Now another group is chlorine. So for the next carbon, the bromine is situated in the right hand side. We have to keep it in the left hand side. So this will be the position of bromine, and we have to fix the iodine for this one. For next carbon, the fluorine is on the above plane and it is situated in the left hand side of the concave. Here you can see it. So we have to place it in the right hand side like this way, and here is also an OH group. So this will be the Fisher projection. Okay, fine. So this is the thing you have to learn. Okay, this is very important in case of RS nomenclature calculation, to how to convert the flying wedge into the Fisher, and we have to stick to the trick that we have to change the position or the direction of the above the plane atom, above the plane group. Now let's discuss about the sawhorse projection. Okay, so sawhorse projection. What is basically sawhorse projection? So in the last lecture, I have given you a chart where I have mentioned that the sawhorse projection is basically a side view, right? How it is a side view. Let's take a look out of it. So let's think that it is a ch3 ch3. Okay, I am drawing a flying wedge type of thing. So it is ethyl and this is chlorine. This is out of the plane bromine and this is iodine. So it is a flying wedge projection, right? This is a flying wedge projection. Now we can see that in the sawhorse projection, what you will look like. What it will look like that you have to rotate the molecule like in this way. Then you will see this molecule like a tilted one. So the methyl will look like this. We have just rotated into the tilted manner. That is why it is a side view. So the ethyl was in the above the plane, right? So it will be in the above the plane. Same thing, how you see the molecule. So it is ethyl and below the plane was chlorine. Okay. For the back carbon, above the plane is bromine and below the plane is iodine. Same thing, if you rotate it, it will look like this one, right? If we change the direction of your eye. Now this is represented as this one. Methyl, methyl and ethyl, chlorine, bromine, iodine. Something like this. Same thing, that we have not considered it any dash or wedge notation, rather we have shown it in a line notation. So you have to think, you can look upon this and you will guess that in flying wedge position this must be in the above position, and this one will be in the dash position, and in flying wedge this one will be the above position and this one will be in the dash projection. Okay, so this is called sawhorse projection. This is called sawhorse projection. Okay, so let's look into the model and it will be clear. Okay, so this is the thing. Okay, fine. Let's now try to visualize it. Let's suppose it is a tetrahedral geometry, and this carbon is also a tetrahedral geometry. That means this blue pencil, and this blue pencil are in the on the plane bonds. Okay, this orange is towards you above the plane, this pink is away from you below the plane. Similar way, this red one is above the plane towards you, and this black one, you can see it over here, this black one is below the plane towards me. So this is a flying wedge projection. Okay, this one is C1, this one is C2. You can consider it to be methyl. Okay, now this is ethyl above the plane, this is chlorine below the plane. Like in the same way, this is methyl on the plane, this is bromine above the plane towards you, and this is iodine, it is away from you, that is below the plane. Now you are seeing from, okay, so you are seeing from this end. Now what you are seeing, that there are two y, right? This is containing a y and this is also containing a y. Fine, this is also containing a y. So that is the sawhorse projection. That if I try to move it around here, that this was your above the plane and it is on the right hand side of you. This one is in the below the plane, like in this way, this was above, so it is in the right hand side, this was below, it is on the left hand side. Same goes for the orange, it is above, so it is on the right hand side, and this was below, pink was below, so in the left hand side. So this is the sawhorse projection. It was a flying wedge, you are tilting the model or you are seeing from a different angle, this is a side view, so this is the sawhorse projection. Now there are two types of sawhorse projection are possible, that is, one is eclipsed and one is staggered. So we have to look about the eclipsed and staggered, and then we will move to the next concept, that how to convert it. Okay, so there are two types of show horse possible. One is called eclipsed. From the name itself, you can think that eclipse means one over another, right? And staggered means the opposite one. Okay, so we will see in the molecule, then it will be clear. So uh, let's take a show horse projection. So it is a show horse projection. Okay. It is one type of show horse projection, and another type of show horse projection is also possible, which is like this. So this is all Y, right? In the front carbon it is Y, in the back carbon it is also Y. But in this case, you can see that this is the inverted Y, the back carbon. So in this case, in the first case, we can see, if I name this bond to be A, this bond to be B, this bond to be C, and simply this is D, it is A and it is F. Now we can see that A bond is in the front of D, right? So A and D are in the front, B and E are, B is in the front of E and C is in the front of F. Fine, you can visualize it, right? If I place 2Y, then it will just cover up the back bond as well. So we can see A is in front of D, B is in front of E bond, and C bond is in front of F bond. But here you can see it is A, it is B, it is C. Let's suppose it is D, E, and F. Now you can visualize it in a way that this bond is in between of D and E, B bonds are in between of D and F, and C bonds are in between of F and E. If you want to visualize it with the help of model, then just see this molecule. So I was telling the eclipse conformation, right? Okay. Okay, let's see. So it was the eclipsed one. So 2Y, you can see 2Y, right? C1 and C2. Now all the bonds are just covering the back carbon, right? This one is in the front of the orange one, this black one is in the front of pink one, and this blue one is front of the sky blue one. Right? So this is the eclipse form. But just rotate it and see this one. So the orange one is in between of the red and black one. This blue one, this sky blue one, is in between of the red and deep blue one, and this pink one is in between of the green, sorry, this blue, deep blue, and the black one. So this is the staggered form. Okay, so this is the eclipse form where every bond is covering another bond. So that means that front carbon bond are in the front of the back carbon bond. But here you can visualize, you can see all the bonds clearly, but here you are only seeing the front carbon bond. Okay, so this is called eclipsed and this is called staggered. So there are two types of projection possible for eclipsed, for the show horse projection. Two types of thing. So this is called eclipsed and this is called staggered. So they are basically interconvertible with CC bond rotation. So if we do CC bond rotation, they can be interconverted. Okay, so let's look in the CC bond rotation and interconvertible between the interconversion between eclipsed and staggered conformer. They are called conformers. Okay, so let's see the eclipsed conformer. So in the eclipsed conformer, both will be Y, right? So both are Y, but in the staggered conformer will be inverted. now we have to now have an idea about the rotation. So we have to rotate this CC bond. This is C single bond C bond. We have to rotate it. Now for rotation we have to fix one carbon and rotate another carbon. So we are going to fix the front carbon. So it is fixed. Okay. Let's give the substituents over here: methyl, chlorine, bromine, and here we are fixing this carbon, so methyl, chlorine, and bromine. Nothing will change. But we have to change the back carbon. So let's give the substituent over here. So here it is methyl, ethyl, and fluorine. Now to get the inverted Y, as it is the eclipsed one, we have to convert it to the staggered one, and in staggered one the back carbon will be the eclipsed the back carbon will be inverted Y. Okay, the front carbon is same. So for the inverted one, you know that this angle is 120 degree, right? These all angles in sawhorse are 120 degree. Now let's rotate it 60 degree clockwise. How we can rotate it? If it is 120 degree, then this part, if it is 120 degree, then the half of it will be 60 degree. Fine. So the half will be 60 degree. That means we are just rotating clockwise. Okay, so this CC single bond we are rotating clockwise with an angle of 60 degree. That means we have to rotate it halfway of 120 degree. That means this ethyl will come here in this position, because this position is 60 degree, which is the half of 120 degree, right? This is 120, so this angle will be 60 degree. So we are rotating in a clockwise way like the steering. So ethyl will come in this position, this fluorine will come in this position, because we are rotating only 60, that is half of 120, and this methyl, which is situated over here, it will come on this position. Fine. So now the position will look like this one, like in this way. So okay, here will be the methyl, here will be the fluorine, and here will be the ethyl. So let's see the substituent. So ethyl was over here. Let me draw the previous one as well. And okay. So initially in the eclipse form, the groups were over here, right? So in this position there was ethyl, in this position there was fluorine, and in this position there was methyl. But upon rotation of 60 degree clockwise, it will come in this way. So the ethyl right now will be situated over here, because this angle is 60 degree, because this whole angle is 120, half of it will be 60. Now we are rotating clockwise, right? The arrow is the clockwise direction. Ethyl will be here and the fluorine will be here, like in the same way, and methyl will be here. So we are forming the staggered one, right? So we are forming the staggered one, and we can erase the dotted part because it is no longer there, right? It is no longer there. Okay. Delete. Cut it, and this one also no longer there. Okay, oh fine. Okay, okay. Only this part. Okay, so it is not possible to remove that. Whether we can erase it now. So you can see this part is to be staggered. So there are basically two types of. So this is look like this one, right? This one is inverted Y. It is the simple Y. So this form is staggered. So we can see the rotation along the CC bond rotation. we are getting the interconversion between staggered and eclipsed form, and basically we will try to rotate it in a 60-degree multiple. That is, we can rotate it 60 degree, 120 degree, right, 180 degree, and so on. And upon the rotation of 360 degree, it will form the same molecule like the starting one. So it is the bond rotation of sawhorse. So in the next video, we will be discussing about the conversion of flying wedge to the fisher one without the trick, by forming the sawhorse projection in intermediate position. Then the thing will be clear. So thank you for watching this video.